Good morning and welcome you all to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 2 DER Integrated Distribution Network Modeling. In the last class, we have seen the bus injection power model of the distribution network, and today we will continue with that power model, but the other one, that is branch flow model or BFM. The branch flow model is generally used for power flow in the distribution networks, where we considered the bus voltages and power flow in the lines or the branches in the network, rather than considering the power injection at the buses, what we took for BIM. But for BFM, we take the flows, power flows in the lines. It is mostly suited for radial and weakly mesh network. That is, you have to keep in mind, you cannot use BFM model for transmission network or very highly meshed distribution network as well. The primary consideration to build this BFM model is that your network is fully radial or you have little bit of mesh, that means 1 or 2 loops are there, not more than that. Otherwise, if you have highly meshed configuration, then it is better to go with BIM model. But if you have a radial network, then your BIM model will not converge properly or it will not give you proper result. So, at that time BFM is more promising. So, BFM uses line level variables such as active and reactive power flows, line current, voltage drops to model the system. This makes it more aligned with physical structure of the distribution feeders. Okay? But there is a consideration, or you can say an hypothesis behind it, that your BFM is only numerically stable model when the network possesses high resistance to reactance ratio. That means your R by X ratio is very greater than 1. That is only possible for your distribution network. That is not true for transmission network. So, your BIM is an universal model that you can use for even for low R by X model, or you can use for higher R by X model, both. But for BFM to use, your network, you will not work for low R by X ratio network. So, similarly, we will start with the BFM formulation. Let us say this is your bus N, this is bus M connected with the 3 phases. You have impedance. Previously, we dealt with admittance. In the BFM, we need not to calculate the admittance matrix, we will directly do the analysis with the impedance values or the impedance matrix. So, this is your impedance, mutual impedance values. Voltage at bus N, that will be a 3 phase voltage, current flowing through the 3 lines are 3 quantities for 3 phases. Then your voltage is given by Vn angle of theta and current is given by Inm angle of phi, that is your line current, and this is your bus voltage. Okay. Your line impedance, that is itself is again a 3 cross 3 matrix, because you have mutual coupling in between the phases, and each and every component of this Z matrix is R plus Jx. Okay. So, in the BIM model, we started our analysis with the KCL equation, right, but for BFM model we will start with the KVL equation. So, the bus voltage Vn is equal to this drop plus your receiving end voltage. So, if you take the receiving end voltage at the left hand side, then Vn minus Vm equals to Znm into Inm. Okay. Then branch power flow equations. How much power it is flowing? That is your voltage multiplied with current, not only complex conjugate, but also conjugate transpose. Okay, because it is a matrix operation. So, you have to take the Hermitian value or the complex conjugate transpose values of the current. So, now expand it. So, your S is a 3 cross 3 matrix. Let us say we are considering it for now, you have mutual coupling even in the powers as well, then V and then current of your complex conjugate transpose. So now power injected to this bus M from bus N will be how much? You are sending this power SNM, and the reaching, how much will reach after the loss? You negate the loss from the sending end power, and you will get the actual power received at the receiving end. So the power going from bus M to bus N or reaching at bus N is SNM minus ZNM multiplied with the square of the current. Now we are dealing with the complex and a matrix form of the complex number matrix. So this will be I multiplied with I complex conjugate transpose. Okay, this is your power loss term. Okay, so now we'll do the matrix multiplication. If you extend it, then the equation will look like this. Then you do this matrix multiplication, and each and every multiplication of this, that means I n m a star and multiplied with I n m a, this will give you the L n m a. The angle will be cancelled out, because this is plus angle, this is minus angle, add it, angle will become 0. So, this is only a real value. Okay. So, these quantities are all a square of the current magnitude. That means, it will be I n m square. Okay. This one is I n m square for each and every quantity. So, then we can write it as a matrix form, that S n m minus Z n m L n m. Okay. So, keeping this, if we write the each and every component equate from left hand side and the right hand side, then we can write that S n m minus Z n m, this is your power, net power coming to bus M. So, the power balance equation at bus M is how much power is coming here. Then this is the net power, that means here if you have a load or maybe a DER. So, how much is the net amount here? That means, if it is sending SDER value and it is consuming S load value, then your S net is S load minus SDER. Okay. So, this is your net value, and then how much power you are giving as an outgoing to your next or neighborhood buses. Okay. So, this is your power balance equation. Now, we will determine the voltage equation. We will start with the same power equation, that is V and I complex conjugate transpose. From there, you determine the complex conjugate transpose of I and put that value to your voltage equation, that V n minus V m equals to Z n m I n m. Put that I n m value and you will get this. Now, take magnitude square at both the side, because you have complex number here. So, and everything now still it is a non-convex and non-linear model. So, we are more considered about the square or the magnitude value of the voltage in the branch flow model. So, take square of it, then you have to take the magnitude and square of it. So, we know the complex number identity, which says if A and B are complex number, and if you take magnitude square of it, then you will get mod of A square plus mod of B square minus A complex conjugate of B plus A B complex conjugate. That is the complex number identity we all know. So, if we use that identity here and expand with this equation, then we will get that V m equals to V n square, that is the first term, that is the A square. Then we have B square term, that is this term, this will become your B and this will become your A. So, A square, B square, then you have A star B and then you have B A star. Okay. This is your A star, this is your B, this is your A and this is your B star. Okay, got it? Now you do the simplification, take the square out of it, and this is your final expression for square of the voltage magnitude. Okay. So, this is your voltage equation and you have got your power balance equation. Now, you have to establish the relation between voltage, current and power. So, you can see that this is the square of the voltage. So, this multiplied with the complex conjugate of Vm star, you will get Vm. Similarly, S is V into Inm star. You can write it like this, that Vm Inm of Vm star Inm star, right. So, if you multiply this to multiplication will give you square of voltage, this to multiplication will give you the complex power, this to multiplication will give you the complex conjugate power, and this to multiplication will give you the square of the current. So, if we represent this equation or this matrix form, let us say this is your matrix Y and this is the complex conjugate of that same matrix. So, this is Y into Y star. Now, for any non-zero vector x, if we multiply x star m, that means this matrix with x, then we will get that the value is y star x square mod, y star x whole mod square. That is, obviously it is a square term. So, it cannot be lesser than 0. So, it is always greater than equals to 0. That means, this matrix M is a positive semi-definite matrix. It is not a positive matrix or positive definite matrix, because positive definite matrix only it holds if it is greater than 0, but here it is greater than equals to 0. So, it is a positive semi-definite matrix. Okay. Now, determine the determinant of this matrix M. So, we will get VNM into LNM minus multiplication of this square and SNM, SNM star and SNM, this will give you the SNM mod of SNM square. So, V is voltage square, L is current square. If you do this two multiplication, then you will get, and with the power term you will get the determinant to be 0. So, you are getting 0 determinant for a matrix. What does it mean? It means that number of linearly independent rows for that matrix is lesser than the actual number of rows present in that matrix. And number of linearly independent rows in a matrix, that defines the rank of that matrix. So, here as it is 0, so the rank of M can never be 2. It is always 1. So, the M matrix is actually coming out to be rank 1 positive semi-definite matrix. So, your actual branch flow model will have a power balance equation, you have a voltage equation, then again you have a matrix which actually a rank 1 positive semi-definite matrix. So, what is the challenge to deal with the 3-phase original formulation of the BFM? First thing, obviously the non-convexity of the power flow equations. The power flow equation has more nonlinear and non-convex term, especially when modeling power losses and voltage drop, which makes the computation intensive. Then this rank 1 constraint imposed for a solution is very difficult. You cannot add it in the analysis part. So, how to deal with this rank 1 constraint? But you have to obey it. If you do not obey it, then you are not obeying the power flow relation between the voltage, current and the power. That you have to obey, because that is the physics of the network. But imposing this rank 1 in a mathematical way for solving, let us say, an optimization problem is very difficult. So, how to deal with this rank 1? Then it cannot be applied for the mesh network, what we already told. Again, it is very complex for 3-phase system. As you have seen that already the size of the problem is going bigger and bigger, and with the mutual coupling this will become very huge. So, how to deal with this? And this will become further challenging when you go for large size network. That means, let us say you go for 8500 or 9500 or 10,000 bus network with 3-phase system. You cannot imagine the size of that problem, and solving that within a very less time, or even solving that in a tractable way, that will be a very complex and a strenuous task. So, for doing that, we do the simplification of this branch flow model. For doing the simplification, we will take certain assumptions. What is the first assumption? The first assumption we will take that the phase voltages are assumed to be exactly 120 degree apart. That means, there is no voltage angle unbalancing in the network. They are exactly balanced as far as the voltage angle is concerned. Moreover, it is assumed that a degree of unbalance in voltage magnitude is also not large. That means, the voltage magnitudes are also close to each other. Both conditions are valid, as we have mentioned, as per the ANSI limit, which says that the voltages should be as nearly as possible, and the network will always be running at a proximity of a balanced system. If your unbalancing is also there, but it will be close to a balanced system. So, with this, if you take the consideration, this will make the off diagonal elements of your power equation, that means this equation, this term will become 0. So, you have only diagonal term associated with the power flow matrix. So, if you use that and expand that one, then you will get the active and reactive power flow equation like this. This is your incoming power, this is the loss in the network, then this is the reactive power incoming, this is the reactive power loss component, then you have net active power, then how much active power is going out from the bus to the neighborhood buses, similar to the reactive power as well. But still in this equation, you have cos phi terms, current angle difference and cosine and sine of it. That is also a nonlinear term. So, how to deal with that nonlinearity? So, for that we take a second assumption, which tells that angle difference between phase currents are generally remain constant. That is also true. Normally, if we do the load variation as well, the current angle difference, remember this, not the current angle values. We are talking about the difference between the current angles of two phases, that more or less keeps on, we normally it keeps as a constant value. So, if we consider this and this term as a constant, so at that time this equation will become a linear equation for L variable, when your variable is L, not I square. Remember this. This is linear for the variable L. Okay? So, the same assumptions we can impose on the voltage equation as well, and we will get this voltage equation which has mutual coupling and everything in place. This is also, these terms are constant. This is also a linear if you take this square of the voltage and current of the voltage values as a variable, not V square or I square as the variable. We will take small v and small l as the variable. So, this equation will be linear for variables small v and small l. Okay. So, this is the overall branch flow model, the simplified branch flow model, where you have 3 linear equations. One is active power balance, one is reactive power balance, and the another is voltage equation. But the relation between the voltage, power and the current, that is still your quadratic equality. That means, if you expand that this matrix, if you expand this matrix and take those assumptions, you will come to these 3 quadratic equality constraints. So, now from very harsh or very complex nonlinearity, which has sine, cos, bilinear terms, so many things. Now you have removed all of them from with some certain assumptions, and then you come up with 6 equations. Among them 3 are perfectly linear and 3 are quadratic. Okay. So, dealing with this is comparatively easier, not completely easy, but comparatively easier. Now, same we will reduce it for the single phase model by just or omitting all the mutual coupling variables or mutual coupling values. So, we will see this is your active power, this is your incoming power minus loss, this is I square. So, I square R is your loss. So, the equals to your net power and how much outgoing power. Same Q minus your reactive power loss is equal to your reactive power net requirement at the bus and your reactive power going to the neighborhood buses as an outgoing bus. This is your voltage equation, and that quadratic equality, because here you have these two are mainly due to mutual coupling, right. This is only for self. So, whenever you go to the balance condition or balance network, this 2 will not be there. So, if this 2 is not there, then you have only one quadratic equality for your balanced network. So, this is the 4 equations you have for your balanced distribution network. But still you have a quadratic equality for balanced and 3 quadratic equality for your unbalanced network. So, still quadratic equality means it is a non-linear or a non-convex expression you have in your system. There is a non-convex. So, you cannot guarantee a unique solution when your system is non-convex. You can only guarantee your solution is unique when it is a convex system. So, for that you need to simplify the non-convex nature of the power flow equation. So, the BFM contains the quadratic terms, especially in the relationship involving voltage, power flow and the current, what you have seen. These non-convexities make the standard optimization problem like the OPF problem hard to solve efficiently and reliably, because you will not get a unique solution. If you run multiple times, you will get multiple solutions with a perfect mu or a standard deviation value, but still you are not getting a unique solution, and until unless your algorithm is giving an unique solution, no one will believe your algorithm. So, for that you need to adapt certain convex relaxation problem that will enhance, that will give you a global optimal solution always, and that will reduce. If you are dealing with a non-convex problem, that is actually a NP hard problem. What is NP hard? That means non-deterministic time polynomial hard. That means you do not know how much time you need to solve that problem. There is no hard and fast rule that this much time I need to solve this problem at every time I run this. If it is an NP hard problem, then this time keeps on varying. So, this if you solve a non-convex problem, then your solution time will change. So, you derived an algorithm and you solved it, let us say you took 25 minutes, and when you sold it to a customer, it took 1 hour. So, the trust on you from the customer will reduce. So, you have to get an problem which is a polynomial deterministic time solution. So, that you get with the convex relaxation. What we do for convex relaxation? Let us say this is your feasible state, we relax it with a certain values. Okay. That means, this is your actual curve, this is the extra amount we take as a relaxation, and we try to superimpose that the global solution will come very close to the actual solution. You will not get the exact global optimality, but at least the proximity of the global optimality. If you can reach that, then your solution will be considered as a good solution, and the solution time will also reduce significantly. So, we will continue with this convex relaxation process in our next class. Thank you.